test number 3 in physics. And our two main topics are energy and momentum. So in the new book, energy, let's see what it is in the new book. So this follows Newton's second law, which allows us to calculate accelerations. Conservation of energy allows us to solve many of the same problems in an easier format. So it's chapter 6 and chapter 7 for energy, and then chapter 8 for momentum. As far as the homework problems are concerned, it's chapters 5 and 6. So conservation of energy, as far as we're concerned, there is the full expression, and really we have two kinds of work. We have non-conservative work, and you also have just work in general. This is one that we typically don't include in the problems that we deal with. We did do it in the lab. This work would be the integral of f dot dx. In the lab, we found the area under the curve of force times distance, and we calculated that. And we could relate that to the increase in kinetic energy. But we have not been including that. So, we usually don't have that involved in our calculations. So the non-conservative work, we'll come back to that. And then you have three terms. One is the change in kinetic energy. One is the change in gravitational potential energy. And one is the change in spring potential energy. Now, typically, it's somewhat rare that you have more than two of these terms that actually are non-zero. So one key thing is to be able to know what terms you can get rid of. Now, the kinetic energy, the change in kinetic energy is just 1/2 mass times velocity squared. So the change in kinetic energy is going to be 1/2 the mass times the final velocity squared minus the initial velocity squared. The change in gravitational potential energy, which is associated with the position relative to the Earth, is equal to the mass of the object times the acceleration due to gravity, positive 9.8 meters per second, times the difference in the heights, h final minus h initial. So the potential energy is mgh, but we're interested here in changes, so it doesn't really matter where you set zero. For kinetic energy, you could get complicated and think about the Earth's moving at a certain speed, and so that there's actually kinetic energy associated with that. But in our normal reference frame of zero, meaning it's not moving relative to the Earth, we don't have to worry about that. So, and then the final potential energy is the spring potential energy, which is equal to 1/2 k, which is the spring constant, times the difference in the deflection of the spring. So this h is different than x. It could be related to somehow. If you think about the bungee cord, this is the total difference in height from end to beginning. This was how much the bungee cord stretched. And so there was a distance where we didn't have any stretch, and then we stretched. So there was some relationship in that particular case. So, if you start from rest, you can eliminate this term. If you end at rest, you can get rid of that term. If you start with the spring uncompressed, you can get rid of that term. Typically, you can't really get rid of one of these terms unless you define your initial or final condition as x equals 0, or the height is 0. So it's not unheard of, but and then the final thing is the non-conservative work. In our case, it's always friction. We're talking about friction as being non-conservative work. So we have negative, and work is force times distance. So we have the friction force times the displacement of the object. So this x here is different than this delta x. This is the deflection of the spring. This is the movement along there. So there are a lot of little sub possibilities where you only have 2 out of the 4 things that you have to worry about. So, for example, I'm just going to give you some demonstrations here. If you have something sliding along a friction surface, in this case there's no spring, so this goes to 0. There's no change in height, so that goes to 0. And what would happen is this thing would move and then it would stop to 0. So our change in kinetic energy, the final velocity would be 0, the initial velocity would be specified, and then you would use the non-conservative work to calculate how far it slid. And in this horizontal situation, the friction force would just be equal to the friction coefficient, the kinetic coefficient of friction, times the normal force. But when you have this horizontal, the normal force is just equal to the weight, which is equal to mass times g. So you can see if I were given an initial velocity, I could calculate delta x, how far it slid. Okay, how about if you just drop something? So just really dropping something like this, or the other case would be if you slide something down a frictionless plane like that. So let me clone that thing there. Oops. So, just something falling here or sliding down a plane. In this case, you do have a change in gravitational potential energy. It's the mass times g times the difference in the heights, final minus initial. And you have a change in kinetic energy, 1/2 m v final squared minus v initial squared. There's no non-conservative work done either here, because we're assuming there's no wind, there's no drag, and there's no friction, and there's no spring. So these are the only 2 things involved. So if I gave you the height difference, you can see actually the mass is going to cancel out when you use conservation of energy in its simplified form. So, if I start from rest, that's 0. I can calculate the final velocity as a function of how much the height is changing, which is the vertical distance. You could have a case where something is sliding along a surface and it's a frictionless surface, so it would keep going on forever and ever unless you hit spring. So we'll put a spring here. So this thing would come along at a certain velocity, would hit the spring, and then the spring would compress, and then you would reach some point where the spring is fully compressed. So fully compressed means for the final condition, that means that V final equals 0. So you start out with some initial velocity, and then you go to 0. So we know the initial velocity, we know the final velocity is 0. Also, uncompressed initially. So if the spring is uncompressed. What that means is that X initial equals 0 meters in terms of the spring potential energy. So you would, again, because there's no friction specified, you wouldn't have any non-conservative work. So the left-hand side would be 0, and the right-hand side would consist of the change in kinetic energy plus the change in spring potential energy. So for kinetic energy, we have what we wrote down earlier, and then you have change in spring potential energy. So for this example I'm giving you, B final is 0, so that term goes out, and X initial is 0. So in this case, mass is important because it doesn't cancel out. That's really the one case where mass is important is when you have a spring. And so you can see that, depending upon what information I'm giving you and what I'm asking you to find, you can solve for K, given the initial velocity and how far the spring compresses. Given K, you could figure out, given the initial velocity, what the final spring deflection is when it goes to 0 velocity. Now, one case, and I'm probably going to put this on the test, so I'll help you a little bit, is let's say that you have a inclined plane. So we're going to have change in potential energy, and then you have a thing sliding down. We've already talked about that. The question is if you have friction. So there's also friction. So this one is going to have some initial velocity. I could give you initial velocity, or I could say it's 0. So just let's say I specified either, if I say it's at rest, then it's 0. If it's moving, it's some value. And I give you mass. I'd also have to give you the coefficient of friction. Say it's 0.3. And so if you look at the three things, we have kinetic energy, we're going to have change in height, we're also going to have a distance. So there's actually two distances involved here. You've got, let's say we're sliding down the plane. So this is the height. This is H initial. This is H final, which we could probably define as 0 meters. So that's H initial, some number. When you calculate the non-conservative work, we don't use the height. We use the distance along this plane. So say it goes here and it goes to the end of the ramp, and we don't say it stops. We just say what's the final velocity. If this starts out at rest and slides, what's the final velocity? If this is initial velocity and the friction is not too high, it'll keep going. Okay, so we'll call this value X. We'll call it delta X, whatever you want to call it. That's the distance over which the friction force is felt. So if we write conservation of energy, we're going to have non-conservative work equals the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy. Well, we can get rid of this one. The non-conservative work is going to be negative the coefficient of friction times, well, actually it's the friction force times delta X. Our change in kinetic energy is 1/2 m V final squared minus V initial squared. Our change in gravitational potential energy is H final minus H initial. So the key thing is, how do you relate delta X? And actually, this would be actually the height initial would be this height here, because we come down to the bottom. So delta x and h are related by the geometry of this situation. So, this is, if I move this over here, that's one side of the right triangle. This is the hypotenuse of the right triangle. So we know that the sine of theta is going to be equal to h initial minus h final. Since h initial is higher than h final, I made that positive, divided by the hypotenuse, which is delta x. So that's where the angle comes into play in terms of the height change. So actually, we can go either way. If we were given delta x, we can calculate the height difference. If we have the height difference, we can calculate delta x. The friction force is not just the weight times mu, because what's important is the normal force. So in this case, the friction force is still mu times the normal force. But the normal force is not equal to the weight. It's going to be equal to the weight times either the cosine or the sine of the angle. I'm not going to tell you what that is. You got to think about it, but just think that if theta is 0, then these should be equal to each other. So which of the two, the sine or the cosine, is 0 when the angle is 0? Is the sine of 0 or is the cosine 0? I mean 1, sorry. So this has to actually be multiplied by 1. So what you want is the trig function such that the value of the trig function at theta equals 0 is 1. Okay. So you get that number, that trig function that's involved here. So as you increase the angle, the normal force should go down because some of that weight is going in this direction and some of it is going normal. So you get less friction force. And you multiply by the distance along the movement of the box. So think about that one. I'm not going to work it out completely. Notice, these are all scalar equations. There's no vectors involved. Velocity, this is the magnitude of the velocity, so it's the sum of the x and y components vector-wise. Height is not a vector in this case. It's just how far above the defined 0 height. Okay, so that's probably the most complicated one. The other ones are going to be one of these kinds of problems where you have 2 out of the 4 things you can get to 0, and then these are the, this is all you really need, and this one right here, to solve any of these problems. Okay, then we have conservation momentum. And I've already worked those out. You have that handout, so there's no point in me redoing all that. The key thing is to know which kind of equation it is, or what kind of scenario it is. So we have inelastic collision. So what are examples? Things like that. You've got the train that gets coupled, meaning there's the couplers that hold it together. You have the Velcro, like we did. You might have a bullet going into some kind of wood or some kind of something that, and it doesn't have to be wood. It could be that stuff they use on Mythbusters to simulate people's bodies. The key thing here is that the final velocity is the same for both things involved in the collision. So if there's 2 bodies, the final velocity is the same. That allows you to just use the conservation momentum equation to solve for the unknowns. You have elastic collisions. Now this is not a totally elastic collision. We had one of these in our homework. This just means that they're not stuck together. So in this case, V final sub 1 does not equal V final sub 2. They bounce off each other to some extent. So if if it's not a perfectly elastic collision, we can still just use conservation of momentum. M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. I have to give you one more velocity. You know, I'd have to give you 3 out of the 4 velocities, and you'd have to calculate the 4th velocity because there's only one equation. So look back in for your homework at that particular example. Then you have perfectly elastic conditions. Collision. And in this case, we have this same equation here, the conservation of momentum, but then we have energy as well, conservation of energy. And that involves, you can get it off your sheet of paper, that involves the velocity, difference in the velocities. In that case, you have 2 equations and 2 unknowns, but you can use substitution, which is worked out on that handout. Don't assume that the handout, you notice I solved for V2 final or something like that, or V1 final, but I could give you the final velocities, and you would have to calculate the initial velocities. So you would have to solve for a different final equation. The initial substitution would be correct. You just have to, you would just have to, well, maybe that same initial wouldn't be right. Yeah, let's just talk about this in case I ask you something other than exactly what's on the handout. And remember, you only have one cheat sheet, so you can't get too much on there. You got to understand what's going on. So let me find the equation because I always get this wrong. Conservation of energy. So that's okay. So the other conservation of energy equation is V1 initial minus V2 initial equals negative V1 final minus V2 final. Okay, so that's conservation of energy. So you've got conservation of momentum. And for our particular case, we were given these, and we were asked to solve for one of these two. Actually, solve for both of them. So if you look at the handout, you'll see that I think I multiplied this out. So I distributed the negative sign to each one of those 2 terms. And I solved for, I think, this one. So I moved this to the other side. So but let's say that I give you the final ones. And so instead of solving for the final ones, you have to solve for the initial ones. What you would do in that case, you would, instead of solving for V2 final, which I think is what I did. So if you look in the handout, I either solve for V1 final or V2 final. If I do that, I'd have that. Okay. And then you substitute that into here, and the only unknown is V1 final. Otherwise, I may have solved for V1 final. But so that was the handout. You can check that out. And then once I make that substitution, I have to multiply everything out and solve for whatever the unknown is. If one of these is unknown, let's say V1 initial, V2 initial is not known, I would solve for V1 initial. So V1 initial would be equal to positive V2 initial minus V1 final plus V2 final. Then I would substitute that into here and do the algebra. And you get a similar expression to what you have on the handout that I worked, but it wouldn't be exactly the same. The other thing about collisions is you got to be careful about the signs. So you have this case, so let's just look at the different scenarios. If this is initially stationary, then we know it's 0. If this one's moving this direction, then we know that V1 initial is positive. If this one's stationary and this one's moving to the left, then V2 initial is negative. So it's moving from right to left. That's going to hit. If they're both, this one's moving this way and this one's moving that way to collide, V1 initial is positive and V2 initial is negative. Now, if this was negative and this is positive, then they would never hit, so you really can't have that situation. Now, when they bounce off, you might get this one go backwards. So initial velocity would be negative, final velocity would be positive. You might hit this, and this one goes this way, and this one keeps going this way. So, anyway, if they say it's moving, use the word right, moving right, then you make it positive. If it says it's moving left, then it's negative. If you get, when you solve your thing, if you solve and you get a positive result, then we know that it's moving right. And if you get a negative result, then you know it's moving left. So you just have to use those results. In terms of your information that's given, you're going to either see left or right. You need to convert that to plus or minus. If you finally get an answer after the collision, if the answer you get is positive, then we know it's moving to the right. If it's negative, we know it's moving to the left. So that's perfectly elastic. And then we have the final one, which is this explosive collision. And what that is things like guns or people throwing things away from themselves in space or on an ice pond where we have frictionless. So what you have in that case is the initial momentum is 0, and then you add your final momentums together, and those have to be 0. So depending upon what you're given, you have to be given one of these velocities, because usually you have both masses. And but I have to give you 3 out of the 4 things here. There's no energy equation that's applicable, so I have to give you 3 out of the 4 quantities: M1, M2, V1 final, V2 final. So I could give you, the most typical one is I'll give you the masses, and I give you one of the 2 final velocities, and then you can solve for the other final velocity. But theoretically, I could give you 1 mass and give you the 2 final velocities, and I could ask you to solve for the second mass. So it's not always as simple as that. So that's pretty much it. We're not going to do any glancing collisions because that just takes too much time. We didn't talk about rocket propulsion, which we may do it. So anyway, these should be easier to do than Chapter 4, and typically people do better on this test than on the previous test.